Okay, we'll move to our final presentation for the evening. Expansion efficiency of a scroll device. Advisor, Dr. Geo Richards. Welcome group, and go ahead and start.
Hi, my name is Henry Brannon, and along with my team, we have worked to find a path to clean energy by determining the efficiency of a scroll expander and how it can fit into an organic Rankine cycle.
Meeting, connecting.
And make sure you're not.
Hello? Sorry about that. Our project presents a unique opportunity as we research a relatively new system and the possible business application that it possesses. A successful system presents an efficient means of power production that is small enough for residential use, but also scalable to commercial application. With the research we have conducted and the available collected data, we are only able to project the economic viability of the system. These projections are quite attainable. Our system has a max capacity of 2.5 kilowatts, but will likely run between 1 and 2 kilowatts. While this may seem like a small output, the production over time has the dual potential of heavily decreasing residential and commercial electricity costs and also working towards sustainability goals for both the consumer and the business. The latter is a huge reason why our system will only grow more appealing in the future. Many companies, such as Grove City Premium Outlets, have sustainability goals they are setting and hoping to achieve in the coming decades. According to their CEO, they, like many other organizations, are rolling out new sustainability goals in 2020 in accordance with climate-based targets. This details how important green energy will be into the future, and while small, our system can greatly contribute to these desires over time. In addition, our system has the potential to greatly decrease residential and commercial electricity costs and even pay for itself over time. Citing a lack of testing and data, projections for the cost effectiveness of our system are produced based on the following assumptions. The system will be assumed to run for 12 hours a day, 7 days a week, which totals to about 4,400 hours each year. The cost of grid electricity will be assumed to be 35 cents per kilowatt hour, a number driven off of the maximum state average in 2019. Finally, electricity consumption will be assumed to be the average of an American household per year at 10,000 kilowatt hours. 3 different models were analyzed, a 1.5, a 2, and a 2.5 kilowatt system, each at different costs. Each system was analyzed over a 15-year period to determine how long it would take for the system to pay for itself. The projections for each system lead to the conclusion that as system capacity increases, buyback period will decrease, even as initial costs rise. This is possible because of low maintenance and upkeep costs due to no fuel being burned in the system, and power being produced through a mere temperature difference from waste heat. For example, an energy company called Electrotherm produces a 75 kilowatt model, which has a capital buyback period of just over 4 years, and an 120 kilowatt system with a buyback period under 4 years. These numbers prove that a scaled system can be cost effective and begin to pay for itself within a short period of time. While some recurring costs may arise over the life of the system, they will be offset by the continuously increasing system savings. One concern for our model is the possibility of system life being less than the buyback period. As far as we know, this will not be an issue, but without the ability to test, a certain conclusion cannot be made at this time. Now I'll pass it on to Austin Krause to talk more about the business goals of our project.
While the production of electricity is the main economic goal for our system, there are other avenues to explore in the growing energy brokerage market. Renewable energy is a critical disadvantage when compared to fossil fuels, and they have an unpredictability in their supply. For renewable energy to be a viable replacement in providing consistent power to the grid, a bulk energy storage system will be required to buffer its inconsistent nature. For example, on this graph, more than enough solar energy is available for harness when the sun is up, so much so that the extra energy produced goes to waste. Also notice that the highest energy demand is when the sun is down. It's this difference that needs to be gapped. Systems like Tesla's Megapack, the world's largest lithium-ion battery, have been implemented to bring the balance to the fluctuating supply and demand of renewable energy. However, batteries take up a lot of energy to produce and are made from toxic resources. Why is this important? Well, that's because our system can play this game too. A major market right now is energy brokerage business. The selling of power back to the grid that was captured and stored from the abundance of cheap electricity on the grid or renewable energy sources at peak hours of production, also known as demand shifting. The profits capable in this market have companies like Great River Energy utilizing the water heaters of 65,000 homes as an energy storage system. What makes our system unique is while it can produce electricity, it also has the unique capability to reverse its cycle and operate as a heat pump. This allows us to also store energy in the form of heat for later use to produce electricity by reversing the system again. This is why testing the system's efficiency is important this semester. In other words, we can store energy in the form of heat during hours when energy on the grid is in low demand and high supply, and therefore low cost. And then during periods of high demand and therefore high cost, our system can efficiently produce and sell electricity back to the grid for profit. This is why this is an asset to the many homes and businesses that utilize renewable energy sources, such as solar panels, to produce energy, because they can store otherwise unused energy produced when the sun is up and use that energy when the sun is down, or sell this stored energy back to the grid for valuable credit. Our system also has the potential for large-scale applications for businesses such as foundries that produce enormous amounts of heat. With a system like ours, businesses that already produce heat as a byproduct of manufacturing can instead use the heat to produce electricity for profit. All these applications truly highlight the dynamics of our system and the growing need for energy storage in a world full of renewable energy systems. And I'll pass it on to Rebecca Jones, who will begin to explain the work we've been doing this semester.
Hello, my name is Rebecca, and I'm the team leader for this project. This is a multi-year project and was presented to us as such. Our portion of the project would involve research and development of a rudimentary system that can be modified in future years. Dr. Richard had a list of requirements that he presented to the team before we got started. Then, together with the rest of the team, we came up with this list of deliverables. First, a business case study to explore opportunities for waste heat recovery and estimates of needed efficiency performance for commercial success. That was just presented to you by Henry and Austin. Next, a process flow diagram and zero-dimensional model showing the thermodynamic states, pressure, temperature, and mass flow rate of the working fluid before and after expansion. Then, based off that, a detailed model would be decided upon and an instrumentation layout would be developed. An analysis of uncertainty within the instrumentation would be conducted, as well as a hazards analysis. Operating procedures and design of experimental test plan would be developed. And finally, due to all of us being sent home due to COVID, publication of data. However, this was not achieved. Finally, the $3,000 budget for production of our design. First, a little bit about scroll compressors. A scroll compressor is a compressor that has fewer moving parts and less torque than reciprocating compressors. It works in a circular motion, where one scroll is fixed and the other orbits around it. As it operates, a pocket of working fluid, in our case air, is slowly compressed or expanded depending on the operating direction. As shown in this video, the scroll is working as a compressor and it is compressing the air as the top scroll oscillates around the bottom. The reversible aspect of this compressor is another bonus. We did not run into anyone in the literature who was looking into this topic from the reversible standpoint. We found a small scroll compressor from Air Squared that used air as a working fluid. It was important that the expander was small so that we could keep up with the necessary flow rate supplied by the shop's compressed air line. Although we are using air as a working fluid now, future years working on this project will switch to refrigerant. This will be beneficial as they convert our rudimentary system that we developed into a full organic Rankine cycle. Now I'll pass it off to Christoph Henschel to talk more about our system design.
Hello, my name is Christoph Henschel, and today I will talk to you a little bit about the components involved in our organic Rankine cycle system. For this setup, we decided on a standard pipe inner diameter of 1/2 inch. Starting at the beginning of the system, we have a 1/2 inch piece of tubing screwed into the piping network, allowing us to connect our system to the machine shop compressed air line. Next, that feeds into a pressure relief valve followed by an emergency shutoff valve. These are put in place to prevent anything from going wrong within the system. If the pressure in the line exceeds 125 psi, the pressure relief valve will open up and relieve pressure in the line, ensuring that nothing will affect the rest of the system. Also along this line is Schedule 40 steel piping, allowing us to connect different pieces of equipment and continue the line towards the compressor, providing an appropriate length for the mass flow rate sensor in the process. The rest of the line leading into the compressor involves sensors that David Alleman will be talking about later. Following the sensors, the system is attached to the scroll compressor via a specialty size pipe connection on the outlet port of the compressor, with the opposite side being our standard piping size of 1/2. Directly exiting the compressor, there are a similar specialty size pipe connection on the inlet port of the compressor, followed by more sensors for readings after the air goes through the expansion process. After the sensors, a line for the machine shop compressed air line is connected via a quick disconnect socket to a male thread pipe in order to somewhat heat the exhaust air coming through the system, preventing any safety concerns that may arise from the colder temperatures. Following the machine shop airline connection, an exhaust piece is attached to the end of the line. This exhaust piece disperses the exhaust air as to not create a high-powered stream, lowering the sound decibels in the process. Through this whole system, there are various adapters used to connect the different pieces. First off, the thread reducers allow us to attach a quick disconnect adapter to the piping network. Then we also have T connectors, and lastly, to fit the pressure and temperature sensors in the system, pipe manifolds. These manifolds allow easy connection of the sensors to the system. The entire system rests on a cart built out of T-slot aluminum framing and is 28 inches wide and 36 inches long, so it is capable of fitting through doorways and elevators. Also connected to the system is a load bank of 5 250-watt light bulbs wired in series and plugged into the generator to apply the power coming. Now I will hand it off to Alec Bonnet, who will be talking to you about pressure losses.
Hi, my name is Alec Bonnet, and I'm going to be talking about pressure losses for our system. Pressure losses were an important thing to look at for this experiment because the system was limited by Grove City's shop air compressor, which has a maximum output of 125 psi. The pressure supplied to the system is too low due to pressure losses. Operating speed and power output may be too low in order to adequately test the scroll. All of the calculations for the initial pressure losses were based on the theoretical numbers from the 0D model. This model assumed that the system would be operating at an air pressure of 115 psi, temperature of 300 Kelvin, and mass flow rate of 0.02 kilograms a second. Based on these conditions, all air properties and head loss coefficients were taken from a fluid mechanics textbook. Our initial calculations were based on 1/2-inch diameter hose and yielded a pressure loss of less than 1 psi. While we initially planned for all the hose in the system to be a 1/2 inch, in our initial setup, the hose that connected our system to the shop's air supply was only a 1/4 inch. This and the small diameters of the quick disconnect couplings used to connect this hose led to huge pressure losses in the system. With the expander running at only 15 psi with the 1/4 inch hose, the max power output we were able to generate was only about 2 watts. After changing this hose feeding the expander to a 1/2 inch diameter hose and removing the 2 quick disconnects, we were able to achieve around 70 psi at the expander and generate enough power to successfully ignite all 5 heat lines. So in final, our setup consisted of 30 feet of hose, 2 4-way connector manifolds for the sensors, 2 elbow connections, 1 volumetric flow meter, 1 pressure release valve, and 3 connectors. As you can see on this plot, the pressure losses for the 1/4 inch hose are substantial. With the adjusted system specifications, the pressure loss program in MATLAB calculated an overall pressure of 4.23 psi. Which is very similar to the pressure loss that we experienced during our final testing sessions. This is down significantly from the 55 psi we experienced with the 1/4 inch hose setup. Now I'm going to hand it off to Kenton Geyer to talk about safety.
Hi, as Alex said, my name is Kenton Geyer and I'm here to talk about safety. This has been one of our top priorities for this project and had to be due to having a pressurized system and components spinning at high RPMs, creating a potential for serious harm. There are 2 main categories in which there were concerns to address: hazards that exist under standard operating conditions while the system is operating properly, and extreme conditions possibly causing failure. The relevant safety concerns while the scroll is operating under normal conditions are pinch points, electrical safety, and noise. The area where pinch points is a concern is in the scroll itself, as that is the only part of the system that is moving. As you can see in the figure on the right, it is designed within an enclosure so that it cannot be accessed while operating. Electrically, the generator is not a concern as it came from air squared already mated with the scroll. As for the wiring we needed to do, We made sure that no wires were exposed or dangerous. For noise, the system is rated to operate at around 65 decibels. While we did not get a chance to test that, we do think that our system runs at or close to that level and think it is well below the safety threshold of 85 decibels. Originally, we were concerned about possible environmental effects of our system. However, since our system does not use lubricant and is run on air as the working fluid instead of refrigerant, there are no environmental concerns with our system. But like Rebecca mentioned earlier, this is a multi-year project that will most likely need to switch to refrigerant as the working fluid, introducing environmental concerns for the future. Under extreme conditions, the main areas of concern are outlet blockage due to ice buildup, pressure failure, and mechanical failure. The outlet air from the scroll is below freezing, so it can cause ice to form from the moisture in the air at the outlet, causing multiple serious issues. In order to alleviate this issue, the air is dehumidified before it enters the system, and there is a port to mix room temperature air with the cold outlet air, raising its temperature above freezing. While running the system, we observed a thin layer of condensation forming and freezing on the outlet of the scroll, but as we could tell, this was from moisture in the ambient air and no ice was building up on the inside. Ice would be more likely to form during an extended test, which is not something that we had the opportunity to run, so this is still somewhat of concern. In order to reduce the risk of a pressure-related failure, the air is regulated as it enters the system, and there is also a pressure release valve and an emergency shutoff valve, as Christoph mentioned earlier. Lastly, mechanical failure is of course a major concern. The scroll manufacturer rated the scroll and generator to run at a max of 3,600 RPM and 75 PSI. So we make sure the scroll is always monitored by at least 2 people while running, and that the system never exceeds this specification. I will now hand it off to David Alleman to talk about data acquisition.
Thank you. Like Kent said, I'm David Alleman, and I'll be talking about the devices that we use to collect the data. Originally, we planned to use and were using a National Instruments DAC to collect the data. However, due to a few issues we were having with it, it wasn't behaving like we needed it to. So when it came down close to the school's closing, we switched to an Omega OMD DAC 55, which is an older model but simpler to use. The Omega DAC wasn't easily compatible with the LabVIEW we were using, so we changed to the Personal DACView software, which easily accomplished the tasks it needed for data collection. The sensors haven't changed since last fall, though we originally planned to use 2 pressure sensors. We actually only used 1, since one of our sensors wasn't functioning properly. Though 2 pressure sensors would have been nice, only 1 is necessary, since with the flow rate sensor and the air density, we can find the enthalpy difference between the inlet and the outlet of the expander with only the temperatures and inlet pressure. This is a screenshot of what our Personal DACView setup looked like. It's very simple and built into the program. We simply needed to select and scale the correct data type of readings. On the left, our readings and controls were displayed, and on the right, a chart plotted our data streams. Data from Personal DACView is saved as a .bin file, and later we would convert it to a text file so it could be easily analyzed in Microsoft Excel. Due to the school's early closure, we didn't gather quite as much data as we had planned to, but what we do have is enough to yield some preliminary results. We conducted 3 data collections, 1 each, with the pressure regulator set at 60, 65, and 70 PSI. This chart shows the temperatures at the inlet and the outlet of the expander, as well as the pressure at the inlet. You can see once the airflow was started, the pressure jumped to about 7.5 PSI below the set pressure, and the temperature at the outlet begins to drop, while the temperature at the inlet remains relatively stable. The other 2 charts look pretty much the same as this one, so I've only included 1 here. The vertical green bars denote the region over which the collected data was averaged, giving us the values we would later use to derive a rough efficiency estimate. It begins once the pressure has stabilized and ends right before the inlet is closed. Next, Micah Nelson will tell you more about the data analysis.
Hi everyone, my name is Micah Nelson, and I'm going to briefly recap some of the mathematical modeling that we did last semester, and I'm going to discuss some of the results of our brief experimentation this semester. Last semester, we were able to generate a mathematical model that captures the geometry of a scroll pair. Using this model, we were able to illustrate the volumes in the various chambers as the scrolls orbit. Additionally, we were able to import this slide into Creo and 3D print a replica of the scroll pair. As David discussed, we were able to take some very preliminary data this semester prior to our exodus. We were able to perform 3 tests, each with an increasing inlet pressure. Pictured here is a summary of that data, which includes the temperatures, pressure, and volume flow rate at state 1, the temperature at state 2, and the power extracted from the generator. Pictured here is a plot of the power generated by the expander on the y-axis versus inlet pressure on the x-axis. Importantly, we can confirm that the power generated by the expander does indeed increase as inlet pressure is elevated. Now, assuming steady flow and adiabatic conditions, an overall isentropic efficiency of the system could be determined given the fluid properties and the power produced if a second independent property at state 2 were known. The overall isentropic efficiency could be calculated as displayed here by dividing the actual power output by the theoretical isentropic enthalpy change from the pressure at state 1 to the pressure at state 2. Unfortunately, we don't know the pressure at state 2, but it won't be hard to calculate next semester when we get a pressure sensor. However, something that we can calculate is the mass flow rate, which will be useful later. The calculation displayed here is pretty straightforward, derived from the ideal gas relation. As illustrated here, the mass flow rates are not huge, but on the order of 1/100th of a kilogram. Knowing the mass flow rates, we can also calculate the energy not converted to useful power, as well as the overall efficiency of our generator expander system. The former can be formalized from a first law analysis, and the latter is a standard formulation of efficiency, i.e. useful work out divided by the total energy change of the system. The results of these calculations are illustrated here. Somewhat surprising are the low efficiencies exhibited by our system, ranging from 22 to 25%. Even if the generator efficiency were at about 80%, that would still only put our expander efficiency at about 30%. Now worth looking at a plot of the values on the previous slide, illustrating just where the energy is going. Note the y-axis is power and the x-axis is pressure. The blue curve is the useful power measured from the generator. The red line is the change in energy output from the system as a whole. The green line is the difference between the useful power out and the total energy change of the system. Immediately, it's clear that only a small fraction, 22 to 25% of the energy change is going into useful work. The rest is being lost directly as heat, lost due to inefficiencies in the expander, or lost due to inefficiencies in the generator. Going forward, future teams should try to quantify these losses and ascertain that all the sensors are indeed working properly. Next, I'll hand it off to Jordan to talk about error propagation.
Hi, everyone. My name is Jordan Luntz, and I'm going to speak on system error, as well as our team's methods for validating sensors and developing procedures. Error goes. So the tolerance on the final expander efficiency, we compare our expander to other tests in literature and understand the viability of a scroll expander within our application. Our research yielded 4 major sources of error in a given sensor system. Accuracy is the sensor's ability to read a value close to the actual value, while precision is repeatability sensor reading. These values are listed by sensor manufacturers and are the sources of error most present in our system. Hysteresis is defined as the delay in a sensor's response to change, and resolution is the smallest change detectable in a system. Both of these sources of error were found to be negligible, as our test runs at a steady state and the resolution is orders of magnitude less than the accuracy and precision of our sensors. Next, we derive the equation for total propagation of error. This equation gives the total error, delta F, that compounds from the error in all of its variables. We are calculating isotopic work and work from a generator, both of which are functions of the multiple variables that we're studying. Our model showed that at the average operating conditions we were using, we expect a 10% margin of error in our calculation of isentropic work, and consequently the expander efficiency. While this might be a wide margin, we are comfortable with the results for limited budget rather than optimization. Lastly, I'll briefly cover how we validated sensors and developed test procedures. To calibrate our thermocouples, we recorded the thermocouple for failing temperatures. We used this data to establish a linear voltage temperature relationship. For the pressure transducers, we made a simple testing apparatus that connected the shop's mainline air regulators with a dial gauge. We then recorded several voltages corresponding to multiple readings and created a best fit relationship between the values. Finally, we developed a procedure. We won't be covering in detail these steps, but the development of this procedure allowed for us to establish testing practices and control unwanted variables in testing, which allows for more reliable results. Next, I'll I'll hand it off to Ken to talk about our budget analysis.
Hi everyone, my name is Luke Hensley, and I'll be wrapping up our presentation by showing you the breakdown of our team's budget and expenses. Like most of the other capstone teams, the Scroll Expander team was given a $3,000 budget for the development of our system. We spent $2,257 on our project, which was well within the financial limitations set on the team. We would not have been able to achieve this without the generosity of the mechanical and electrical engineering departments. And we'd like to thank faculty members on both departments that helped us to cut down those expenses. Shown on the slide here are two Pareto charts that represent our expenses and our cumulative incurred percentage of expenses. The left chart is the estimated expense breakdown if we were to purchase all the supplies that we used, and the right chart is the actual expenses incurred by the team. As you can see, our largest expense was the purchase of a scroll generator assembly, which accounted for 2/3 of our total expenses. The data acquisition card, rolling table, and several of the process sensors were donated to the team by the mechanical engineering department, which seriously reduced the team's required costs. This slide shows sensitivity diagrams that represent the percentage of cost incurred per purchasing category. Again, the left chart is based on the budget model where the team was responsible for all of the purchases, and the right is the actual model of the team's expenses. The most noteworthy expense of the team was the scroll expander, as mentioned before. Finding a low-cost scroll expander was a challenge, as we had a choice between an expensive air-based expander using inexpensive air-based sensors, or a refrigerant-based system that would have required more expensive sensors and equipment. In the end, we purchased the expander that would be most economical while still fitting our needs, and we were still able to stay within our budget. That concludes our presentation. We'll now be taking any questions.
Thank you, group. What we'll do is we'll open up for questions at this time. I'll start off. I have a question for your project. You've got hardware, mechanical hardware, electric software, I guess, or electrical hardware, maybe circuits and so forth, and then software. Of those three, how did your project break down in retrospect, and which of the areas were proved to be the biggest challenge?
I can speak on behalf of the mechanical side. A sub-team and I constructed the cart that the system built on, as well as developing the system itself. It definitely presented some challenges, particularly with flow rate and having pressure losses that we couldn't figure out for a time. But in the end, we figured that we needed a bigger diameter tube and were able to complete the project.
I could speak to that as well, being part of the team that developed the sensors, and David can of course speak to the part where we had to integrate the sensors with a computer, as well as working with the generator. The electrical side of the project was definitely a learning curve, seeing as how we're not really familiar with too much of that stuff. But I think, especially if David was willing to mention it, we kind of got through it and we figured out how to make everything work for sure.
Absolutely. Luke's correct in saying that the electrical part was definitely challenging, at least on our end, being that was our focus for the project. But we did get the new Omega and personal DACV software to work much more easily than I expected to in the end. So it was difficult, but we got there.
Thank you. Any other questions? You can put that up on the text bar there, or just ask your question by activating your microphone. Gio, are you there?
Yes, I am. And there is a
Yeah.
question there from James Brooks on relative efficiency. James, would you mind unmuting and asking that question?
Sure. Yeah, this is really interesting work. I think this idea of a reversible scroll compressor is pretty exciting. Question for you on the efficiency, though. Some of the data you presented shows something like 25% efficiency. I wondered if you could comment on how that compares to other heat engines, like a steam turbine or something else. Is that a surprising number or an expected number?
Yeah, I can comment a little bit about that. Well, that number is pretty poor, honestly, compared to some of the other systems out there. We're really expecting something probably at least like twice that. And part of a good portion of that is probably because of the pressures we were using, potentially the loading. There's a set of optimal conditions that a lot of mathematical modeling goes into finding, and it can be kind of sensitive depending on that. And part of what we were planning to do the second half of the semester was the actual testing and trying to figure out what happens in terms of like speed. Like, so you can have, if you load it like heavily enough, you'll get a lot of power out, but it'll rotate a lot slower, and you might have more or less leakage within the chambers. You might have more or less friction generated. So it just, yeah. So to answer your question, it's not very great.
Micah, perhaps you could speak to, you mentioned just briefly, and if you could expand on the idea that rotational speed is critical, because as you know, there's an optimal speed where this efficiently expands, but it's only one speed at a given pressure. And I don't know if you can explain that easily.
Well, essentially there's well, actually, I don't think there's an optimal speed, but there's an optimal pressure ratio between the outlet and the inlet that basically it lets you maximize the amount of work that you get out of the fluid. So if you have too much pressure at the front end, you'll have underexpanded fluid coming out the back that could have been used to produce more work. Instead, it's just being dumped into the air and it's just expanding. On the other hand, if you have a really low pressure, you'll actually have I think I got that backwards. I'm sorry. You'll have, oh wait, no, I got it right. No, if the pressure on the inlet is too low, you'll have overexpanded fluid, and you'll actually have the back pressure working against you even more when you're trying to dump it out. So there's an optimal pressure ratio that lets you just exactly match whatever your back pressure is. In our case, just atmospheric pressure.
Yeah, so just to follow up on that, I mean, it seems like having a closed loop control of the back pressure might be beneficial then.
Mm-hmm. Yeah, and it was definitely something we were thinking about, and it would have definitely been a bit more work, especially on the electrical side of things. But that's definitely one of the things that, especially when this gets like integrated into an actual cycle where it is going to be closed loop, that they will have to experiment with and manage.
Good. Thanks, guys.
Mm-hmm.
Any other questions?
This is Gio Richards. Could I jump in and just ask the team to speak to the connection to our entrepreneurial school? Because I don't think that was made today.
Yeah, I can speak on that. So basically a briefing of that, which is kind of cool. Me and some other people on the team were able to work alongside with two entrepreneurship majors, Ethan Hayward and Nathan Rogers, for their senior projects, but for the entrepreneurship department. So given the business aspect of our project, I thought it would be a cool way to get some more research done and some groundwork done on kind of the business analysis of the system. And so, yeah, they built a complete business plan and are actually doing the Wolverine Venture Battle, or the version that they're doing given the quarantine with that. And then, yeah, so that was also a really cool dynamic in addition to the project, for sure.
Thanks.
And just one more thing to add to that, through a connection of Austin's, we were able to meet with a man in town in Grove City, Lee McCracken, and he works in the power brokerage business. And he was able to provide some real world insight into what we were doing. And that really helped with bridging the gap between us and the entrepreneurship students. So that was really cool that Austin could connect us with him and maybe work with him in the future for this project.
I had a question about the budget analysis slide that's up there, and I think you mentioned this in the beginning of your talk, but I had to step out of the room. It looks like your actual versus estimated cost breakdown basically changed because you had a donation of a data acquisition card. Was that what happened?
Yeah, that's correct. So we had a couple parts donated, actually. The data acquisition card was donated by the department. There were a couple sensors left over from the old refrigeration board that we ended up taking, and the mobile table, the table that we put on casters. We essentially used some scrap T-slotted framing and some old aluminum plating from the back of the shop. Put it up on casters and didn't have to spend any money on that either. So that's where the differences come in between these two.
Thank you. That makes sense. We have time for one more question. Any final question? Okay, hearing none. Again, I'd like to thank you for your presentation for the Scroll device group, and congratulations again on finishing this. This concludes our first evening of presentations, and we will join you all tomorrow night. Good night.